Okay, I'll start today's class. So until now, we've been doing various random variables and trying to understand their distributions coming from experiments. So let me just recall a little bit. So let me just recall. Let me recall. So what have we been doing? We've been taking. We start off with a sample space S. So S was a sample space that we had, and this we thought of as all possible outcomes of an experiment. Then we had what's called an events, a set of all events. As of now, we took events as all subsets of S. Then we had a P, which is a probability on the sample space. And now what we did was we said, okay, fine. Now, so each of these was connected to an experiment, and sample space was thought of as all possible outcomes of the experiment, all outcomes that come from the experiment. And you could think of even the experiment as selecting one outcome from the sample space. And events are quantity interested in, and P is the chance that a particular event might occur in an experiment. That's what we Then we went and say, okay, fine, I have to keep on changing sample spaces again and again. So I defined this concept of random variable, which is function from S to the real line. It's a random variable. So as of now, I have not defined it for all possible sets S. So I will think of it S as when S is discrete, and S is countable or finite. Then this will actually imply that the range of S also is countable. Range of X is also countable. And we would call all these random variables as discrete random variables. Now the next thing we did was we said, okay, fine. Now each random variable is characterized by two things. So one was the range of X, which was some subset of the real line. The other thing was what for any X in the range of X, we wanted to know what the chance that X was equal to X. And this we defined as what's called the probability mass function of X. This we called as this function F from F of X from the range of X to 0, 1, we called it as the probability mass function. And the whole idea was that this essentially, if I know the range, if I know the chance that how each values on the range are distributed by X, this would give you what's called the distribution of X. And this would be enough to understand very few. So now I want to go back and see, okay, this is one way of understanding random variables. You know its complete distribution. So you know exactly what's going on, what value it takes, and so on. So now I want to sort of build on this a little bit. What I want to do is I want to now go back to an earlier question that we asked long time back. So the question I asked long time back was the following. I said, I don't know if you recall this question, way back in the Bernoulli trials. I asked this question. I said, I think this is an example 2.1.2. So it's example 2.1.2. I asked this first question. I said, on an average, how many successes will we have? Will be there after n trials? And this is a very natural question to ask. You know the chance that how k successes in n trials is given by the binomial. That's easy to understand. But how do you understand this question? How many successes will be there on an average? So this is what we will try and do now. We'll try and this is the focus of this chapter, which is called. So the key, what I'll try and understand is the key summaries of. So I'll just call it as chapter 4. I'll be summarizing discrete analysis. So the topic of this section. So let's go back to a very old idea that we have in our heads. That is, so suppose I give you a bunch of numbers. So how do you find an average in such? So let's say we roll a die, right? So, and then we have a. So let's say we roll a die. Let's go back to the old idea of an experiment. We roll a die. The outcomes are 1 to up to 6. So then you want to know what's the average outcome. Right? So what's the average outcome? So so the earlier one would be what you would do is you would just take so if you have numbers 1 through 6, we all know our conventional idea is the following. Right? You take 1 plus 2 plus 3 plus 4 plus 5 plus 6 by 6. That's the average. And this we would compute it to be 3.5. That's what you would get. But then you can just rewrite this calculation a little bit. Let's see how one would do that. Let me do this. So what one would do is one would split this up as 1 as the values the random variable takes or the roll of the die takes 1, 2, 3, 4, 5, and 6. And then I would think of it as 1 into 1 by 6 plus 2 into 1 by 6 plus 3 into 1 by 6 plus 4 into 1 by 6 plus 5 into 1 by 6 plus 6 into 1 by 6. So it's the same as the top guy. There's no difference. I just read it in the whole. So now, what does this perspective give you? This perspective says that you weight each outcome of the roll of the die according to the probability of its occurrence. Right? Outcome according to the probability of its outcome. And that's what this is. This line is saying. So now the idea is that if you take a bunch of numbers and do your average, you're giving the chance that every number appears equally in your list, which is the same as the roll of a die experiment. But what happens if you have a list of numbers where every number doesn't appear equal? Like you could have random variables like binomials take different values for different. Something let's try and understand it. So that this is a motivation. So what we could do is we could take a list of numbers. and if you have a probability distribution of them, the average value would be the weighted sum of those numbers, and the weights being the probability of the outcome. Excuse me. So now that comes to our first definition. That's the first definition. Let me write that definition down. So here's definition. So here let x be from S to T be a discrete random variable. So automatically I know that S is discrete. That is, so we write this down just for confirmation's sake. That is, S is countable or finite. So it will automatically imply that T is countable or finite. Finite. And what you want is you want to know the expected value. So then the expected value of x is written as E of x. So written as E of x. So I'll use square brackets E of x, and is given by so the formula is the following. So what you do is you sum over all possible values. X takes values in T. So range of x is in T. So what you do is you sum over all possible values in T, and then you multiply the value T, and the way to give the sum is way to give the number is the chance that x is equal. Okay. Of course, this sum is if T is finite, it's well defined. Otherwise, it's a series. It's a series, right? So you have to caveat by saying that this is equal to this, provided the sum converges absolutely. So provided that the sum converges absolutely. So in this way, in this particular case, when this sum converges absolutely, we say x has finite expectation. X has, I'll write it as finite expectation. Okay, now, very nice. So the idea is clear. So when this sum converges, we say x has finite. Am I still audible? Can you just give me a chat link? Thank you. So now what happens is if the sum diverges. So if the sum diverges, so the sum as this called the series is sum of series sum. So if the sum diverges, then we'll say that the random variable has not had doesn't have expectation. So the way you define it is that if the sum diverges, that it doesn't converge, but it doesn't go to infinity, but not to infinity. So a series can not diverge to infinity, can just happen. We will say, so maybe I'll go first like this. Sum diverges to infinity. So we'll do that first. For sum diverges to infinity, we say that the random variable has infinite expectation. So sum diverges to plus or minus infinity. Then we say we will say x has infinite expectation. In both cases, if the sum diverges neither to plus infinity nor minus infinity, we say that the expected value is not defined. So the sum diverges but not to plus or minus infinity, so it doesn't go anywhere, it just oscillates or something. We say that the expected value is not defined. Expected value of x is not defined. So that's the idea. So you have random variable x, then you define it by the sum. The sum converges, you say that's the expected value. You say that's fine expectation. If it diverges plus or minus infinity, you say that the random variable has infinite expectation. And the sum diverges but not to plus minus infinity. We say that the expected value of x is undefined. So let's do an example now. A simple one just to illustrate the idea. So here's an example. So example 4.1.2. So let's say a random variable takes three values. Let's say x is the random variable x takes three values. So we'll go back to my black pen. Random variable x takes three values. Let's say 200, 20, and 2, or 0, let's say. 0. 0. Such that the probability of x equal to 200 is equal to, let's say, 1 over 1000, x equal to 20, 27 over 1000, and x can take the rest with high probability, x equal to 0, with 972 by 1000. Then this would mean that the expected value of x, by definition, is the chance that is what the chance that t is in t times probability x equal to. So what you do is you just multiply it. Right? So you just have 0, the first one. The probability which it takes is 972 by 1000 plus 20 times 27 by 1000 plus 200 into 1 by 1000. So we add these up, you will get some points up. So on average, x will take 0.74, but notice that this number is not attained by x. Right? So let me just explain these concepts a little bit in review. Let's see if I can get this screen to come up again like before. Split view again. Let me split view again. Yes. I want to go to the first page here. First page here. And here I want to go to the second page. So this is what we've been doing. Right? So the So we start out with the idea that what's a sample space? Sample space S is an outcome experiment, and we had random variables, and we understood them by distributions. But then we want to understand, on average, what value a random variable will take. The way we motivate that by saying that, okay, fine, you think of a rolling of a die experiment, the numbers are 1 through 6. And then if you were to find the average of 1 through 6, the conventional idea would be you sum them up and divide by 6, and then you 3.5. But if you observe that a little bit, that just says that you give the weight 1 over 6 to every number in the list. And that gives you a number 3.5. And this motivated us to the definition of a average for any random variable. We said, fine, if x was from S to t, then and S was countable, then t automatically countable, so you have a discrete random variable. Then the mean of x, or the expected value of x, would be written as sum from t in t, value t, times the probability that x takes the value. And that weighted sum is called the value of x. And the sum is a countable sum, so it can converge or not converge or diverge to infinity. So in these three cases, you define it as, if it grows absolutely, you say, okay, it has finite expectation, and the sum is nicely defined. If the sum diverges in plus minus infinity, you say the random variable has infinite expectation. If the sum does not diverge to any number, we say does not diverge to plus or minus infinity, then we say that the expected value of x is magnified. Okay, now let me go and try and understand some properties of this, of A of x. So the first theorem is that if random variable takes only one value all the time, let's just rule that case out, that trivial case out. Let me do definition. Did this color and then I came back this. So here's the theorem. I called it 4.1.3. The idea is the following. So let x be a random variable, s to c, s to p, such that x of s is always equal to a constant c for some c, right, for all s and s. Then expected value of x is just going to be equal to c. So how's that? The proof is very simple. So let me write the proof down. Hard proof. So proof will be the following: that you just take, you know that the chance that x equal to c is equal to 1. So x only takes one value, c. Then this would imply that E of x is just c times the probability x equal to c, which is just c. It's a fairly simple calculation, c times 1, which is equal to c. So a constant random variable will have its expression as c. So this is written in short as E of c is just c. So expectation of a random variable is constant value. I put the c in for the random variable, you write it as E of c. So that's one thing with this one degenerate case we thought through. The other observation you can also make is the following. Suppose the range of x is finite. So range of x is finite. X is finite. Let's say t equal to range of x is finite. Is finite, then E of x is always finite. Expectation is finite. Then L always, then E of x is like that down. E of x is going to be summation t in t, probability x equal to t is always going to be finite because the finite sum is always going to be finite. So we'll say that x has finite, and consequently and X has finite. Variance. So when the range of X is infinite, is countable, as countable to infinite, then there's a possibility that you could have finite or infinite condition, or you not have infinite consequences. So let's see two examples. Let's see whether this is not valid. So let's say example. So the idea is that suppose X takes a value, let's say the non-negative integers with let's say even one. So let's say the range of X is all the even integers. Let's say 2, 4, 8, 6, no, all multiples of 2, let's say, so powers of 2. And let's say it takes the chance that X, the probability mass function, X equal to 2 power K, we let it be equal to 1 over 2 power. For all K. So it's clear that there's a probability distribution. So then, what's the expectation of X? The expectation of X in this case would just be the sum over T in T, right? T times probability X equal to. That I can rewrite as the sum over K equal to 1 to infinity. Infinity of what? So I have 2 to the K is the value that the thing takes, and then the probability that it takes is 1 over 2 to the K. And so this, of course, I don't know, we'll do it properly. Let's say, how do you understand this sum? So the way one would do it is, you would say, fine, let's say S and N equal to the sum from K equal to 1 to N. So let's go back a little bit. So 2 to the K times 1 over 2 to the K. That's the sum from K equal to 1 to N of the sum number 1. There are N times you're adding 1, so it will be N. So this will imply that Sn would diverge to plus infinity as N. Right? You've seen that. Right? That means this number is going to be infinite. So that means the random variable has infinite. So this means that X has infinite. X has infinite expectation. Let's do another example where we can see that there are some cooked up examples where we do the following. We say that, let's say, I did maroon just to get the color, and I did it. So there's another example. So example, say 4.1.5. Black. Let's see this way here. Suppose X random variable takes, let's say, a range of X is, let's take the negative power. So let's say -2, -2, and then 4. Let's alternate -2, 4, -16, and so on, +16. That is, it's -2 to the power k, whole power. That means, and I do the same thing. Same distribution. I say X is this number, which is -2 to the power k. It takes this value with 1 over 2. It's obviously a probability for k being equal to 1 because the sum sums up to 1. Geometric series. Now, if you want to do expected value, so expected value of X, you would define it again as the sum from T in T, chance at T, and then X equal to T. Okay? So here again, you would write it formally as the sum from K equal to 1 to infinity minus 2 to the power K, 1 over 2 to the power K. So again, what does this sum mean? This sum means what? This sum means you would again do the following. Say Sn is equal to the sum from k equal to 1 to n minus 2 to the power k and 1 over 2 to the power k. And this we know exactly is going to be the same as the sum from k equal to 1 to n. So 2 to the k cancels off and you're left with minus 1 to k. And this we know, if you start with minus 1 and keep adding 1 and minus 1, you get 1 minus 1 for n equal n is odd and 0 when n is even. So this will imply Sn diverges, and not to plus or minus, not to plus or minus, because it keeps oscillating between 1 and minus 1. So that means that, so we just conclude that E of x is not defined. E of x is not defined. So the expectation of x is undefined. It's sort of a nice, interesting fact. Let's see if I can get that also in space here. Let me try that. I'll write this theorem down and then maybe think a little bit how to show it. So this is a nice, interesting, useful mathematical tool. We'll keep on using it sometimes. Here's a lemma. The lemma is the following. So when is E of x a real number? So E of x, let x be a random variable. The discrete random variable. Then E of x is a real number if and only if E of mod x is finite. So this is a sort of a, so what I mean by the statement is that what I mean by the statement, so x is a random variable. So this person here, what I mean by the statement, I take a random variable y, which is equal to mod of x, the actual value of x, and I'm just considering ey. So if ey is finite, then I know that ex has to be finite, and vice versa. It's a nice, interesting fact for random variable. That is, a random variable has finite expectation if and only if E of mod x is finite. So one way should be obvious. I think if E of mod x is finite, then E of x is finite. But let's just try and work out the proof properly. So maybe I'll just do one small thing before I sort of discuss the whole thing. Let me just go to my split view again. Split view. Very nice. The previous page. Here I want to come here. Yeah. So here again, I want to summarize what I did so far. So if x is constant, then E of x is constant. So you write that as E of c is equal to c. The range of random variable is finite, then obviously it's my expectation. If it's countable, then you have two cases. In the first case, in example 4.1.4, we found out that the mean diverged to infinity. So in the second case, we said that we saw that if you take the values in this bracket down here, if it took values minus 2 to the power k and it kept oscillating between negative and positive, the mean was not well defined. And you say E of x is not defined because that series diverges neither to plus infinity nor minus infinity. Similarly, now when can you say a random variable has finite mean? One condition is that if the absolute value has finite mean, as we take y equal to mod x and take E of y is finite, then we can say E of x also is finite. Right. So now I'll just conclude this today in the first class by the following: that when do you what do you mean by E of x, like, physically? Like, suppose if so one thing to think about is the following: all this is fine, all this formula is all fine. But one thing, we'll try and prove the lemma. We'll try and prove the lemma next, in the next class. We'll prove the lemma next class. So proof will be done soon. But what I want to understand is that is let's see the explanation of explanation. So how explanation, or let's say significance. So let me spend a minute or so on this. See, suppose I have, let's say, x random variable, s to t is random variable. And suppose, let's say, let's take for lack of a, let's say, e of x is 4. Let's say e of x, which is the sum from, suppose, t in t, probability x equal to t, is some number a, is some number a is some real. What does it mean? What does it tell you about the random variable? So that's something to think about. So what does it tell you? So what does this tell you? So e of x is just a number a. What does it tell you about x? Something about, you must think about it a little bit, because it's a formula, I know, and also like you, but you can go back to the original definition we had. Right? If you have 1 through 6, we add the numbers up, we get 3.5. So what does the average value of a bunch of numbers tell you? Or for example, for your class, for example, if I tell you that the mean score on the last quiz was let's say 10 out of 20, what does that mean? It gives you some idea. So that you should relate to what a random variable mean is, or expected value is.